All right, welcome back to Organic Chemistry 1 lecture. We are picking up where we left off in chapter 4, and we are talking about how to draw Newman projections here. Now, a Newman projection is just another way to represent a three-dimensional organic compound, and it's particularly useful in assessing the stability of different what we call conformers. So one thing to keep in mind is that with these single bonds that we have in the alkanes, those can all rotate freely, right? Remember, pi bonds are stuck. They cannot rotate because if you were to rotate, you break the pi overlap, you break the pi bond, so that doesn't happen. But sigma bonds can rotate freely because they have their overlap in the axis of the bond. So any rotation around that is allowed and it occurs. So what that means is there's going to be certain ways of rotating that are going to be more stable than others. And using Newman projections is kind of the easiest way to demonstrate what the most stable, what we call conformers are, or the most stable conformations are going to be from that rotation. So that's what we're going to learn about. So what we've learned about already as far as introducing three-dimensional drawings on your two-dimensional screen or on your paper, for example. We've talked about wedge and dash notation, where the wedge is coming out of the screen at you, and you have to imagine that in 3 dimensions. The dash is going into the screen away from you. And so that's kind of one way to look at it. And this is actually a good time if you have your model kit. I recommend just building a quick ethane molecule. So check it out, the black ones are carbon, you know, because they're tetrahedral, and they're tetravalent as well. If you notice, your model kit should have probably like 4 bonds in it. These white ones are hydrogen here, so it's just monovalent. The white ones usually are the hydrogen. And so this is one way that you can represent what an ethane would look like. Looks like this, and this is kind of how we draw it on the wedge and dash notation. You see this hydrogen, that's coming out towards you, so that's going to be a wedge. And then this hydrogen back here, that's coming out towards me, right, towards into your screen. So that's in the dash notation there. Likewise, now here, this is pretty much in the same plane. I know it's hard to see, but this is pretty much in the same plane as this carbon. So this is just a straight line. You draw that in your paper like that. Then this this hydrogen is coming out towards you. That's a wedge. This one coming back in to the screen, that one's a dash. So that's kind of the wedge and dash notation. Now, if we draw in all the hydrogens, that gets really kind of difficult to keep track of. And it's not particularly useful when we're trying to imagine it in 3 dimensions, and we're looking for how to like figure out what the most stable version of this one is. So that brings us to the Newman projection here, which is what we're going to learn about now. And what we do with the Newman projection, rather than looking at it as a side-on view, we're going to look at it down the axis of the bond. So basically, this is kind of hard to do. Let me see here. There we go. So what you see is you have your carbon in front. You cannot see the carbon in back. It's eclipsed by the carbon in front. But you can see, oh, the carbon in front has a hydrogen pointing up, one to the left, one to the right. And in the back, you see there's one hydrogen that's pointing straight down and one to the left and one to the right, like that. And that's going to be represented by what we see here. Okay, so now that's kind of what this slide talks about right here. This is just showing, again, just a closer view of the Newman projection. What you do is you take the compound and you imagine, like, put yourself in the plane and you're looking down the axis of the bond. So, like, for example, if you're looking at it this way, I'm going to turn it around towards you, and now that is what you see right there. Now, in this case, the front carbon has its one hydrogen down, one to the left, one to the right, and up. And then the back one has its hydrogen up. That's this one right here. And then one down to the left, one down to the right. And that's the idea here, is basically you put a big circle in, and then you do the, I don't know, I call it like the Mercedes-Benz symbol. So you've got this here, and then just like alternating behind it, you've got the bonds that are to the back carbon there. So this is a good time to practice. Also, make sure you like get your kit out as well. This is going to help you a lot. And we're going to have a practice problem on the next slide. So again, the way that we can do this is, let me just like draw this one for you so you can see like what it looks like when you draw it. And I am going to cheat. I'm going to use the circle tool here. So you're looking down at it this way. We know we're going to start with a circle. And then from there, I'm going to go ahead and draw. Well, so you're looking at it from this angle. So now this hydrogen is in the plane and it's pointing down. So we're going to point this one down. And I'm going to start from the center because that's the front carbon. I can see this carbon-hydrogen bond because I'm looking at it. It's the front carbon. And then there's one up and to the right and up and to the left. Now the back carbon, I can see that there's a hydrogen sticking up back here. So I'm going to draw it like that. And then down and to the right, down and to the left. Now this one in particular doesn't show you the wedge and dash notation, so it's hard to see how it's going to look, but that's how you're going to end up drawing these here. So now let's go ahead and let's do a practice problem here. One thing you can do is go ahead and build a model of this compound, and you can use that model to help you draw it. So I'm going to just kind of show you what my model looks like. I would recommend you pause the video and then try to do the Newman projection. When we unpause the video, we're going to come back and we're going to do that together. So check it out. So this is, let's see, it's a butane, right? So 1, 2, 3, 4 carbons. There's a chloro on the third carbon as you're looking at it, right? So this is one closest to you. So you're looking at it from this angle. There's a methyl group pointing down. And then over here, there's a methyl group that's pointing into the plane away from you. So you just make a 4 carbon chain. And that's what I have here. 1, 2, 3, 4 carbons. You don't have to fill out the hydrogens on the end ones. I recommend just filling out the hydrogens on the ones that you're actually looking at here. But you know, this is a methyl group and this is a methyl group here. So then the way it's going to look is, this is how it looked for me, but actually for you guys, like coming out towards me. Oh yeah, I'm gonna have to do this a little bit differently if I'm gonna do it for you, but this is how it looks like for me, where I've got now, you can see here, there's the hydrogen on the second carbon in the axis here. We have to assume that's pointed towards us because we know the methyl group is pointed away from us. That's what's back here. Then this chlorine, that's got to be in the bond, in the same plane as that carbon-carbon bond, the one that we're looking down, which is right here. Now this one, this methyl group, as you can see, if you're looking at it this way, that's pointing straight down. So that tells us we need to orient it so that the methyl group is down and the chlorine group is up. Okay, now give that a shot and then we'll do the Newman projection together. So I recommend pause the video. And when we come back, we're going to do the Newman projection together. Okay, hopefully you pause the video. If not, this is what it's going to look like here. You can tell because look, if you're looking at it in the plane, you have to imagine yourself going into the screen and like looking down in 3 dimensions down this carbon-carbon bond axis. So when you do that, you see, oh, I've got a methyl group pointed straight down, and then in the back, I can see this chlorine that's actually pointed up. So now let's go ahead and draw that Newman projection. So again, I'm going to cheat. I'm going to use the circle tool here, like that. And then start just doing what you notice here. With the front carbon, I can see that I've got my methyl group down. So methyl group down, and we're going to just do CH3. I don't have the ability to do subscript here, unfortunately, so I can't show you that. But just know it's CH3. And then we have these 2 hydrogens up and to the right and up and to the left. So that gives us another set of things here, H, and over here, H. Okay, now look at what's happening in the back. So the first thing, the easiest thing to do is probably to draw in the chlorine in the back. So that chlorine is directly up. So we're going to draw it in like this. Cl. Okay, easy enough. And now let's go ahead and look at these other 2 substituents that are in the back. Now down and to the, sorry, I have to look at it from my angle, down and to the left, like this. That's where we see that methyl group. So you can see it because it's to the left of this methyl group here as you're looking at it. I hope this works out in the mirror image. I can't remember if they mirror the camera or not. This is going to be even more confusing. And then down over here, down and to the right as you're looking at it, that's going to be where the hydrogen is over here. So like that. Now we can move it around to make it a little nicer, like that. Okay. Okay. All right. So that's what your Newman projection should look like. Now I can't remember. Do we have some more practice here? Let me check on the next slide. Clear drawings. There we go. Okay. All right. So why don't we go ahead, take a break, try to draw these Newman projections, and I'm going to walk you through it when we come back. So let's pause the recording. I'm gonna have the answers up when I press record again. So just be ready to kind of go through the answers at that point. Okay, and we are back. So now looking at this first one, we're looking down this, again, carbon 2, carbon 3 axis. So this is like C1, C2, C3, C4. So it's C2, C3. That's going to be our front carbon is this carbon 2. The back carbon is this carbon 3. And don't worry, we're not naming this at this point. Technically, you could think of this as carbon 3 and this is carbon 2, but don't worry, that's not, we're just like identifying what carbon is our front carbon and what's our back carbon. So now if we're looking at it from this angle over here, if we like imagine this in 3 dimensions, so we rotate it out towards us, or we put ourselves in that perspective, well, so carbon 1 here, it's bonded to a chlorine, and it's bonded to a methyl group, and then there must be a hydrogen as well. This methyl group, as we're looking at it over here, that's going to be pointing straight down because that's in the same plane as the carbon 2, carbon 3 bond. Whereas this chlorine here, that's actually sticking out of the screen. So if we rotate ourselves around now, we're looking at it from this angle, that's coming out, that looks like it's to our left. So sure enough, the methyl group we write on the bottom here of the front carbon, and the chlorine we're going to write on the top left, like this. And then the only thing that's remaining is the hydrogen. That must be on the last remaining spot, which is here on this side. So, okay, so now that's the front carbon. The back carbon has a methyl group, it has a bromine, and then it must also have a hydrogen. So as we orient ourselves in 3 dimensions, we're looking at it down that axis. The bromine, or I'm sorry, well, let's start with the methyl group. The methyl group is pointing straight up because it's in the plane of the paper or the plane of the screen, depending on how you're looking at this. And that's pointing straight up. So that methyl group for the back carbon is going to be pointing straight up. The bromine is pointing into the plane of the paper. So as we go around here, we see, oh, the bromine is to our right now. So it's bottom and right over here. And that leaves one spot for the hydrogen, which is over here to the left and out. That's actually pointing towards us as we're looking at it in this screen. Okay, I hope this makes sense. I know it's a lot of 3-dimensional thinking. I really recommend building these models and playing with them there. And that's going to help you out a lot because we're about to start rotating these things and it's going to get complicated. So make sure you get some practice here with these sample exercises. Next up, we're looking at the bottom portion here. The front carbon here, again, is bonded to chlorine. It's bonded to a methyl group. The methyl group is pointed straight down. So sure enough, that means that we're going to draw the front carbon so that its bond is pointed straight down and it's attached to a methyl group. Then the chlorine is pointed out at us. So as we orient ourselves in that direction, we notice it's pointing up and to the left. So like, sure enough, that's where we write that. The only thing that's left is a hydrogen, and that has to go in this last spot, which is pointing into the paper. So that would be like the dashed wedge there. Then we look at the back carbon. The back carbon is going to be alternating here because we see this carbon-chlorine bond is in the plane of the screen. So as we look back there, that means that chlorine is going to be pointing straight up, and that's where we have it right here. Now that leaves us with a methyl group that's pointed in towards the paper, into the paper, and then a bromine that's pointed out towards us. So as we like go in through here, okay, the bromine is pointed out into the left. So I'm gonna write that down here, this bromine down here. The methyl group, which is going into the plane of the screen, that's gonna be out into the right. So that's how you can think about these Newman projections. And again, this is going to give us a lot of important structural information as far as identifying what is the most stable orientation for these compounds. So let's go ahead and let's talk about that next. Okay. So that brings us to conformational analysis. So that's kind of the deal with Newman projections. We want to be able to identify which of these conformers is the most stable. And so the first thing that we have to do is we have to define a term which we call the dihedral angle. And the dihedral angle is basically the angle between one of the front substituents, so this one here, and the back substituents here. Now this is all a circle, right? So if we think of it as like 360 degrees, and then divided by 6, that comes out as a 60-degree angle here. That's what we call the dihedral angle, or sometimes the torsional angle as well. This is one particular conformation, but as we said, these can rotate. So there's no reason that you can't actually have these like this, where all of a sudden now you look at it and they completely line up right over one another. Here now the dihedral angle is 0 because they completely overlap. So we have to like define these two different positions. These are the two most important positions. We have what we call the staggered conformation. That's what we've been drawing so far. So that's where you have the 60-degree dihedral angle. And you can also have the 0-degree dihedral angle, where everything is we call this the eclipsed conformation. If I do it right, you can see the front hydrogen eclipses the back hydrogen. You can't see the back hydrogen. That's why we call it the eclipsed conformation. So once again, that's the staggered conformation. That's the eclipsed conformation. And of course, you can have anything in between, like these bonds can freely rotate, right? But the two extremes are going to be the staggered and the eclipsed, and that's going to define a lot of what we see here in this conformational analysis. Now, the reason that this becomes important, and right away I'll tell you, the staggered conformation is the lowest in energy. So again, that's sorry, it's hard to do sometimes. That's this one right here, where you have this 60-degree angle. And the reason for that is that we think of these hydrogens as like little points, but remember, the carbon-hydrogen bonds involve electrons, and electrons are negatively charged. So they take up more space than just what we draw on the paper. So they're occupying a large amount of space. As negative charges get closer and closer together, they repel each other harder and harder. That's your electromagnetic force. So as you go from the staggered conformation, well, that's as far away as those bonds are ever going to get, right? As soon as you start rotating towards each other, it's going to get, either way, it's going to get less and less and less of the dihedral angle until you get to the eclipse conformation. And here, you have a very significant overlap of these bonds where they're repelling one another. So the most stable conformation is going to be when they're as far away as possible in the staggered conformation. So the word that we use to describe this repulsion of the bonds, carbon-hydrogen bonds that we see here, this is what we call torsional strain. And in the case where you have 3 carbon-hydrogen bonds that are all overlapping, in the case of ethane, that difference in energy is 12 kilojoules per mole. So this is what it looks like basically, if you can imagine like rotating it around, rotating it around, rotating it around. Basically you go from very low energy, staggered conformation, to the high energy eclipse conformation. Then as you keep rotating another 60 degrees, okay, that goes to the staggered conformation again, then to the eclipse conformation again. Another 60 degrees, now you're in the staggered, 60 degrees again, eclipsed, 60 degrees again, now you're in the staggered. So I recommend just kind of playing around with your model here and seeing how that actually works. As you can see, it actually, yeah, just keeps going. It's a circle, right? So I can just go infinite times around. Okay, now what we're going to do is we're going to basically break up that total 12 kilojoules per mole. And the way that we calculate this is basically calculate the energy of the eclipse conformation, subtract the energy of the staggered conformation. And in the case of ethane, that's 12 kilojoules per mole. Well, we can associate roughly 1/3 of each interaction of this like torsional strain with the 3 interactions that we have here. So we have a carbon-hydrogen bond basically conflicting over here, another carbon-hydrogen bond from here to here, and then a final carbon-hydrogen bond here to here. So that's where we have these conflicts. So we divide it by 3. We're going to go ahead and assign, when we have a hydrogen-hydrogen eclipsing interaction, we'll say it's about 4 kilojoules per mole. So having a total cost of 12 kilojoules per mole means that we can actually predict the equilibrium that we would expect to see between staggered and eclipsed. And it turns out that about 99% of molecules should be in the staggered conformation at any given time. Another 1% will be in the eclipsed conformation. So again, that's just a math that you can do using the thermodynamics that we learned last semester. Okay, now I don't think this is a necessarily totally important slide here, but we can, as long as you understand that those are conflicting here, where you have these bonds here, there's also some theoretical underpinning where basically the antibonding sigma molecular orbital can overlap with the bonding molecular orbital of a neighboring bond in the staggered conformation. That could be a reason that you get an extra stabilization for the staggered conformation. That's kind of theoretical. So yeah, don't worry about that one too much, but it is kind of like theoretically true that like when we run calculations on molecular orbitals, it seems like you can get some overlap between a bonding sigma molecular orbital and a neighboring anti-bonding sigma star molecular orbital. And that leads to like a little bit extra stability. Okay, now let's look at propane. So go ahead, make a thing for propane. Now this time you don't really need to do, so I've got carbon 1, carbon 2, and then carbon 3. Just like when we did the Newman projections earlier, I didn't put the hydrogens on carbon 3 just because we're using this as a stand-in for a methyl group, and it can be kind of difficult to put those on there. So now the difference is going to be when we look down carbon, so we're going to have carbon, here we go. We're going to look down the carbon 2, 3 axis like this. As we can see, we got the methyl group on the front. Here's the staggered conformation. You know that's more likely than the eclipsed conformation. We just imagine rotating around. So there's the eclipsed first one, the second staggered one, second eclipsed one, third staggered one, third eclipsed one, and then we're back to where we started. So again, you just go around infinite times. Now this time when we analyze the conformational energy that's lost by going from staggered to eclipsed, turns out it costs about 14 kilojoules per mole now to go from staggered to eclipsed. That's the difference in potential energy. It looks very similar to what we saw for ethane because all of these eclipsed interactions are the same and all of these staggered interactions are the same. So if we have this barrier to rotation, that's 14 kilojoules per mole, well, we know that, let's go ahead and take a look. We know that each of these hydrogen-hydrogen interactions, so the one on the right here, the one on the left over here, those each cost 4 kilojoules per mole. That adds up to 8 kilojoules per mole, but the total cost is 14 kilojoules per mole. That means that the torsional strain from the hydrogen methyl group interaction must account for the rest of it. In other words, 6 total kilojoules per mole. So that's what we're going to use as our kind of guide marker for what the torsional strain due to a methyl group interacting with the hydrogen is going to be. So again, hydrogen-hydrogen interaction, that's going to cost 4 kilojoules per mole. Hydrogen methyl group, that is going to be 6 kilojoules per mole. Okay, now, what gets more interesting is when you do butane. So butane, oh, here, I'm just going to go ahead and swap this guy out. You can use one of our previous models because we did a butane before. So once again, I've got the hydrogens on carbon 2 and carbon 3, but carbons 1 and 4, I'm just going to leave as a black marker there to note that these are methyl groups. So it can start out in kind of the lowest energy conformation here, which is where you have the methyl group in front opposed to the methyl group in back. So as you can see, the methyl group here points up, the methyl group down here points down. That's as far away as they can get from one another. And that's going to be important for what we will look at here. Because as it turns out, when we go to the first eclipsed conformation, that costs 16 kilojoules per mole. And when we go to the second staggered conformation here, all of a sudden, we're not back where we started. So here, we started down here. We actually have, when we go to the second staggered conformation, we don't have the same dip. We have still a relative barrier of 3.8 kilojoules per mole here. Then we go one more, and we have an eclipse conformation again. This is our second eclipse conformation. But this second eclipse conformation is even worse than what we had before with the first eclipse conformation. So there's a greater energy cost, a greater torsional strain for being in this eclipse conformation than when we were in this eclipse conformation. Can you think of why that might be? I'll give you 2 seconds to think about it. Again, here we go. This is our first eclipse conformation. It does not cost as much as this eclipse conformation. Why would that be? Pause the video, think it out. Well, hopefully you noticed they're not the same, right? Here we have two different hydrogen methyl group and hydrogen methyl group eclipsed interactions. Those are going to each cost us 6 kilojoules per mole, as we found out previously. Here, rather than having that, now we have two hydrogen, 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 and now we have a methyl group interaction. As you can imagine, methyl groups are much bigger than the hydrogens that we were talking about before. So they take up more space. They're going to cause more repulsion. They're bigger clouds of electrons. So that's going to be a problem. And sure enough, that is accounting for an additional 3 kilojoules per mole strain that we see on this eclipsed versus this eclipsed. Now we go back around and everything else is symmetrical like you would expect. Again, this third staggered conformation is not as good as our first one because what we're going to talk about next. And then we have another eclipse conformation that matches what we saw in the first eclipse conformation that we did. And then we're back to where we started with our most stable conformer, which is where we have the opposed methyl groups here. Okay, so as we mentioned before, the difference between this staggered conformation here and this staggered conformation here is about 3.8 kilojoules per mole. Now, the reason for that, as you can imagine, maybe you've imagined so far, is that these methyl groups are going to be so big as far as their electron clouds go. Even when they're staggered from one another, they're still going to have some amount of torsional strain with the way that they interact with one another. So these electrons clouds are repelling these electron clouds up here. And so you get that torsional strain. So we have a special word for this. This is what's called gauche. This is a gauche interaction. Remember, these are eclipsed interactions like that. This is what we call a gauche interaction, a methyl group gauche interaction. Gauche is like French for left. It's just like when they're kind of close together, you can think of it that way. And yeah, it's just this steric strain that's imposed when you have a really big group staggered next to 60 degrees away from another big group. So again, we have these. The other thing that we need to define here is when it's not gauche, when we have this staggered conformation where we have this front methyl group up and this back methyl group down, that's what we call an anti-conformation, anti. So they're anti to one another, and so they don't have any interactions with one another. And that anti-conformation is going to be the most stable one. Okay, so this gives us like a little clue here, because the next thing that we're going to have to do is we're going to need to be able to draw Newman projections of the most stable conformation and the least stable conformation. The most stable conformation, that's going to occur when the biggest groups are anti to one another. And the least stable one, that's going to be when the biggest groups are eclipsing one another. So just keep that in mind. Yeah, so we already found out before, remember that hydrogen-hydrogen eclipses are 4 kilojoules per mole. So if we draw our least stable conformation here, what that means is, if you just kind of do the math here, we have two hydrogen-hydrogen eclipsing interactions to the left and to the right. So that costs 8 kilojoules per mole. What's left over is 11 kilojoules per mole. That is going to be the cost of the methyl groups here. Okay, and this table kind of gives you a chart for the relative energy of conformation cost for each type of interaction. So when you have hydrogen-hydrogen eclipse, that costs 4 kilojoules per mole. Hydrogen-methyl group eclipse, that's 6 kilojoules per mole. Methyl-methyl group eclipse, that's 11 kilojoules per mole. And then methyl-methyl gauche, that's about 3.8 kilojoules per mole, like that. Okay, all right, so that kind of gives us our idea. So now what we want to do is go ahead and draw the lowest energy conformer for both of these as a Newman projection, and you're going to look down the C2-C3 bond. So I noticed here I didn't put an arrow before for this one, so let's go ahead and draw it from this angle over here. So I'm going to go ahead again and pause, and I'll draw the answers. I'll pause the recording, draw the answers. I recommend you pause the video at this point. We'll go over the correct answers when we come back. So just a moment. Again, give it a pause, answer the question. We want the least, lowest energy conformer. And actually, you know what? Why don't we do both? Let's draw the lowest energy and the highest energy conformer for both of them. That way we get a little extra practice before we move on. So pause. All right, and we're back with our answers here. So the key is here basically for the lowest energy conformation, you want to pick the one that has the least amount of repulsion in the gauche interactions. Unfortunately, you don't really have much of a choice here, other than you want to make sure that you have basically 2 CH3 gauche interactions. If you put the CH3 down here, you're going to end up with 3 gauche interactions. So this was the one that minimizes that. The highest energy, of course, that's where you're going to have the worst eclipsing conformation. So that means methyl group on methyl group, methyl group on methyl group. So there you have your worst eclipsed formation. Then down here, again, with our lowest energy, we want to reduce the interactions. There's some question as to like chlorine, how does it deal? Chlorine is about equivalent with a methyl group. So anything bigger than chlorine, like a bromine, would be worse. But for now, we're just going to stick it opposite. We're going to give ourselves the best anti-conformation possible, which is chlorine to methyl. That does leave us with 1 gauche interaction here, but there's no way to totally get away from that. So, you know, you do your best. And then over here, we just set it up for the worst one that we actually have a eclipsing methyl group chlorine interaction, because that's the highest energy conformation. Okay, and that's what we got for Newman projections and conformations here. Stick around. The next video, we're going to talk about conformations in cyclohexane molecules. So see you soon.